Hey, it's Mr. Lum, and we're going to be doing the August 2006 Chemistry 12 Provincial exam for some practice to get ready for our final exam. Anyways, let's jump into it. And anyways. Okay. First question, which of the following would not be units for reaction rate? So just to reemphasize is that reaction rate has to be something over some unit of time. So grams per second is acceptable, concentration per second is acceptable, and or concentration per minute, and even pressure measured over a unit of time is acceptable. But mass over mole, this is not acceptable. Okay. Next question says, what is the rate of aluminum consumption in moles per minute if 0.98 grams of copper are produced in 2.5 minutes? So I'm going to be going 0.98 grams of copper, and that is produced in 2.5 minutes. I keep it in minutes just because it wants the answer in minutes, so I'm not going to be changing into seconds. Now, it wants me to change it to moles, and more importantly, it wants me to change it into aluminum moles. So the first thing I'm going to do is change grams of copper into moles of copper per minute. So I'm going to go 1 mole, and I look up the molar mass of copper, and I found the molar mass right here is 63.5. And so I'm going to go 63.5 grams right there of copper. So effectively what's happening is that my units are canceling out, and now I'm in moles per minute. But I'm in moles per minute of copper. And I want to have moles per minute of aluminum right there. So I'm going to do my mole bridge, and I want copper to cancel out. So I'm going to go 3 copper, and that is equal to 2 aluminum right there. And if I cancel all my units out, copper cancels with copper. And now I'm in moles of aluminum per minute. And I grab my calculator and go 0.98 divided by 2.5 divided by 63.5 times 2 divided by 3. And I get 0.0041, or in other words, move the decimal places over 3 times. So 4.1 times 10 to the minus 3. And again, we said that's moles of aluminum per minute. Okay, next question. Which of the following describes what happens to the kinetic energy and potential energy as an activated complex forms into a product? So I'm just going to draw some type of enthalpy over time kind of graph right here. So this is enthalpy, or essentially this is potential energy, and this is time right here. Our activated complex is at this point right here. These are reactants, and these are products right here. So as we have our activated complex turning into products, our potential energy has to decrease. So the potential energy has to decrease. Now, what is that potential energy turning into? Well, those particles are getting faster after they've coming off of the activated complex. They're moving faster. So that potential energy is converted into kinetic energy. So in other words, since potential energy is decreasing, that means kinetic energy has to increase because total energy remains the same. One of the principles of thermodynamics. So kinetic energy is increasing. Which one has the 2 check marks? Is that one right there. Okay. Number 4 right here. Increasing the concentration of which of the following substances would cause the greatest increase in the reaction rate. So first thing we should be recognizing is that this is our rate determining step right here. So if you found a catalyst for step 1 or a catalyst for step 3, it won't make a difference in the reaction rate. But if you found a catalyst for the second step, since it's the rate determining step, that would make a difference for the reaction rate. Same thing, anything that we do to speed up the slowest or the rate determining step will increase the reaction the most. So if we want to make the reaction faster for the rate determining step, or in other words, this slow step right here, we should probably be increasing the reactants of these things. So which one of them are reactants? Well, we have that H2 as a reactant. What about NO? Can NO be done? No, that will increase the first step, which is not a rate determining step, so that won't help. What about N2O? N2O is right here. It is for step 3, and that won't help. And also, it's also an intermediate. So what that means is that step 3 is almost fueled by the production of the products from step 2. What about H2O? H2O is just a product, so that actually won't do anything for this thing. So that's our answer right there. Number 5, which of the following are products in the overall reaction? So let's find out what are the products right here. And so I'm just going to zoom out just a tiny bit. And I'm just going to erase a couple of these things right here. Now, when I like to do it is that I like to cross things off like that. Okay. N2O is right here. Yeah, and I think that's the only things that are crossing off right here. So what this reaction is 2 NOs plus 2 H2s turn into 2 H2Os and an N2. So our two products look like our N2 and H2O are things. The other two that are listed there are actually reaction intermediates. So 1 and 4. Which of the following are the values for the activation energy and the enthalpy in the reverse direction? So the reverse direction is exothermic. So since we're exothermic in the reverse direction, we have to be dealing with something that is going to be negative. It's starting at 200 right up here, and then it's decreasing by 50 to go down to 150. So we know our answer is going to be A or C. And so now we also have to find out what is our activation energy in the reverse direction. So we're looking for the distance or the difference between these things right here. So 200 to 300, and that's a 100 difference. So it's going to be that one right there. Okay, number 7. If the above potential energy diagram represents a reversible reaction that reaches equilibrium, which of the following must be true for the forward direction? So we don't really know anything what's going into this reaction right here. But what we do know is that we know the change in enthalpy. And the reactions want to go towards minimum enthalpy. So in terms of enthalpy, that wants to go in the reverse direction. Because in the forward direction, it's endothermic, and the reverse direction, it's exothermic. So we know that enthalpy wants to go in that direction right there. So if it were going to be an equilibrium reaction, entropy must be going in the forward direction, because that would cause an equilibrium. If entropy was going in the reverse reaction, that would be a non-spontaneous reaction. If enthalpy and entropy were both going in the forward direction, then that would be a completion reaction and no equilibrium would be established. Everything would turn into products. So we have to have these two opposing forces, enthalpy going in the reverse, entropy going forward. So first off, we do know that enthalpy favors the reactants because it favors minimum enthalpy, so it's favoring the reactants right here, and these things are the products. So enthalpy favors the reactants. So we know the answer is going to be B or D right here. Now, in order to get that equilibrium established, entropy needs to favor the products, and entropy reactions favor maximum entropy. And so that means products need to have a higher entropy. And so as in the forward direction, the entropy needs to be increasing. Okay? And that'll cause an equilibrium. Okay. Consider the following diagram for the equilibrium system. Which of the following stresses was applied at time 1? So right here, the first thing when you see everything kind of going in a different direction and no spiking up or spiking down, and we have just two things, KEQ cannot be equal for these two numbers, right? Like if we took, so KEQ is this number divided by this number right here. And if the numerator becomes bigger and the denominator becomes smaller, there's no possible way that KEQ can remain the same. So the first thing you should realize in a situation like this, it has to be something changing in the temperature. So the temperature had to change because KEQ cannot remain the same value under these conditions. So we know it's not A and B. Next thing is that we see NO2 has increased and N2O4 has decreased. So we know that it's a shift to the right, okay, because we have more products right here. So what's going to shift it to the right? Well, if we increase the temperature or increase the energy, it'll shift to the right. And that's going to be our answer right here, is the temperature was increased. Okay. Styrene is manufactured as below. We have some energy right here. Which of the following describes the temperature and pressure needed for the maximum yield of styrene? So we want to make this stuff right here. So we want it shifting to the right. Okay. So if we increase the temperature, that'll make it shift to the right. So the first thing we should say is that we want to have a high temperature. Okay. Now, the next thing is that we're dealing with all gases right here. We have two gases on this side and one gas on that side. So if we increase the pressure, well, the reaction is going to want to make less pressure, or in other words, it's want to go to something that makes less pressure. So if we increase the pressure, it's going to shift it back into this direction right here. And so we don't want that. So what we want to do is we want to decrease the pressure. So if we can lower the pressure, the reaction is going to want to make more gas. So, so we want a nice low pressure. And that's our answer right there. Okay. Consider the following reaction. Now, this one's a little bit tricky, and it's kind of like made there to like catch the people going a little too fast. So, which of the following lists the reactions in order from greatest concentration of oxygen at equilibrium to the least concentration? Now, an important thing is that we have to see what our KEQ is. So first off, we have solids here, we have liquids right here. So none of these things are going to go into your KEQ expression. So for reaction number 1, KEQ actually equals the concentration of oxygen. Now, you have to put the coefficient as a exponent. And even though we have a coefficient of 0.5 or a half, that still goes as an exponent. So you can write a half or you can write 0.5, something like that. Okay. Now, for KEQ for the second reaction, it's just the concentration of O2. And for KEQ for the third reaction, it's just the concentration of O2 again. Okay, they have no coefficients in front of there. So in other words, what these things are going to be, since they actually give us the KEQ, is that this is going to be 2 times 10 to the minus 25, 5 times 10 to the minus 29, 3 times 10 to the minus 14. Okay. And so what is the concentration of O2? Well, for this first one is the only one you actually have to do any math on. So what I'm going to do is I'm going to essentially, to get rid of this right here, what you do, this is the same, like taking to the power of 0.5 is the same as saying it's root, like that. Okay, how do I get rid of root? Well, I have to square it. So I'm going to square both sides. And so if I have to square this side right here, okay, so 2 times 2 is 4, and times 10 to the negative 25 times 10 to the negative 25 is times 10 to the negative 50. So this value is actually going to be 4 times 10 to the negative 50. I didn't erase that a little bit. There we go. Okay, so now that we've calculated the concentration of O2 for all of them, which one has the greatest concentration of O2? Well, it's 3 has the greatest concentration. Okay, and then it's 2, and then it's 1. So 3, 2, 1, right there. Okay, next one right here is that we have in a 5-liter container, there's a whole bunch of these things. We have CO2 right here. We have some 1 gram of calcium carbonate and 1 gram of calcium oxide, and which is the following value. Now, again, a little bit of a tricky thing. Make sure you watch your subscripts. We have solids right here. So KEQ is actually just equaling the concentration of CO2. Okay, so now all we have to do is find out what is the concentration of CO2. So I'm just going to be taking 2.42. All of these numbers are they're useless now because we do not need them because they're solids. So we have 2.42 grams of carbon dioxide. I want to change this into moles. So 1 mole. Oxygen has a molar mass of 16. There's 2 of them there, so that's 32. And carbon is 12. 12 plus 32 is 44. Okay, and so if I do this, I'll get moles of CO2. Okay, I don't want moles of CO2. I want molarity of CO2. So I have moles, and now if I divide this whole thing by the amount of liters, which is 5, I'll get my concentration. So 2.42 divided by 44 divided by 5 equals, and I get 0.011. And that's my answer right there. Consider the following. Initially, we have 0.31 moles of carbon tetrachloride, and at equilibrium, it's we have some Cl2 in there, 0.06. What is the following? This is actually an ice table question. You don't see a lot of ice table questions in the multiple choice section, but here we are. We have CCl 4, and that forms an equilibrium with carbon and chloride. So 2 Cl2s. That's not my best straight line, but we're just going to live with it. We have a solid right here, so we're not going to be doing anything for that one right there. Initially, the only thing that's thrown in here is the carbon tetrachloride. It's a 1 liter container, so 0.31 divided by 1 is 0.31. So it's, yeah. And that implies that there's no chlorine added into it. At equilibrium, though, we do have some chlorine gas in there. So we have 0.06 molarity. So what did it had to this had to increase by 0.06. Now, since we are a 2-to-1 ratio, this one had to decrease by 0.03 molarity, and that makes this 0.28 molarity. So now I'm going to throw this into my KEQ expression, and KEQ equals the products, which happen to be, again, we're not putting carbon in there, so that's going to be 0.06. And since we have that 2 there, that's squared over 0.28. And that's not squared because there's only a 1 as a coefficient in front of that. Into my calculator, 0.06 squared divided by 0.28 equals 0.0128. I got KEQ equals 0.0128. Or in other words, 1.28 times 10 to the minus 2. Or 1.3. That rounds to 1.3. Yeah, 1.3 because of the sig figs. Everything is 2 sig figs in there. Okay. Number 14. Initially, NO2, some NO2, N2O5, and NO were all placed in a container allowed to reach equilibrium. When equilibrium was established, it's found that the pressure had increased. Okay. Which of the following explains what happened? Okay, so here we have 3 gases, and here we have 2 gases. And so what we found is that they just threw in a bunch of chemicals into some kind of container, and they shook it up, and then they found, and they started to let it sit. They found that the pressure started to increase. So what happened was, since the pressure is increasing, it had to shift to the left. Okay, it made more gas. More gas means more pressure. Okay, so we know that this thing is shifting to the left. So we know it's going to be this one or this one. Now, why would it shift to the left? It would shift to the left because there's too many products in there, and so it had to shift to the left to create reactants so that it can reach an equilibrium. So there's too many products in there. And if we know that KEQ as products over reactants, if we had too many products in here, this is too much. That means our trial KEQ was too high. Our trial KEQ was too big, and it had to come down and have less products. Okay, so we know that our trial KEQ was bigger than our KEQ. Our trial KEQ was too big. Yeah. So, anyways, that makes our answer that one right there. Which condition is essential to prepare a saturated solution of an ionic salt? So if you want to make a saturated solution, or in other words, like an equilibrium solution, what you need to do is make sure that you have solids turning into aqueous, and you also need aqueous turning back into solids right here. And that is, well, look at this. That's the symbol for equilibrium right there. So you better make sure that you have, like in your beaker of a saturated solution, you better have some solids sitting at the bottom. Now, how do you have solids sitting at the bottom? Solids or solute, you better have a lot of that. So you have to have excess amount, so much that it actually can't dissolve. And so if you have an excess amount, then you'll have a saturated solution. If you have any amount of solute, well, then that means you could have an unsaturated solution. temperature of 25 degrees Celsius. This thing only applies if you want to be using the data tables that are provided for us. And a fixed volume of solvent, no, I don't even. That's just wrong. Uh, every different amount of solvent will have a different amount of solute that can dissolve in it. And just like temperature, different temperatures can have different amounts of solute that can dissolve in it, but they can still have saturated solutions at whatever volumes or, yeah. Anyways, which compound will have the greatest solubility? We got COS, CUS, FES, MGS. COS, CUS, FES, MGS. Okay, let's go down here. COS, FES, I already forget them all now. MGS, I'm supposed to have 4. COS, not carbon monoxide. COS, FES, MGS, and there was one more. CUS. Okay. So let's take a look. Okay. COS. So here's, we're dealing with all sulfides. So COS is low soluble. So I'm going to write low soluble right here. That means it's not high soluble. FES is also low soluble. MG, soluble. Okay, so that's looking like our winner. And CUS, that's also low soluble. So that's going to be our answer right there, is MGS. Oh, not in the right order that I wrote it in. Okay, MGS is our has high solubility. Okay, what is the net ionic equation for this reaction? BAS and BeSO4. So when we combine these two things right here, we're looking for what kind of precipitate is going to form. So let's look for, we have BAS and BeSO4. So let's go back to here. We have, I forget it already. BAS, BeSO4. BAS, BAS, BeSO4. Okay, so barium sulfide. Let's take a look at beryllium. Beryllium sulfide is not is soluble, so that's not going to be it. And let's look at barium sulfate. There it is, barium sulfate. That's low soluble. Okay, so barium and sulfate are going to be low soluble, and that means they're going to be forming our precipitate. And so everything else is a spectator in this case. So barium and sulfate are going to be forming our precipitates. Everything else, Be and S, get rid of them, because we're dealing with the net ionic equation. That means get rid of anything that is not part of the reaction. So for this lower one right here is the complete ionic equation. This one is a formula equation right here, but it's actually wrong, because BES is not going to be forming a precipitate. And this one's also wrong. BES isn't forming a precipitate, so my answer is this one. Okay. Which of the following substances will have the least effect on the equilibrium in a saturated solution of PbI2? PbI2 turns into Pb2 plus 2 iodide minus. Okay. So if we added HI is going to increase the concentration of I. That'll make it shift to the left. Okay. If we had Na2S, is Na is soluble with everything. Is S going to react with Pb? Let's take a look.